Welcome to the data science class offered by DataBricks here at Spark Summit West. So we have two instructors for you. My name is Doug Bateman, and this is Waleed. We'll introduce ourselves here just momentarily. What I first want to do is give you kind of an idea of what we're going to be doing today. So we're going to start out, we're going to review DataFrames, which is really the most powerful API when it comes to Spark in terms of its ability to query and process data concisely and easily. We're going to see what that means. And in Spark 2.0, DataFrames will be upgraded even further by being unified with a newer approach called data sets, and I'll mention that a little bit later as well. We'll then go in with a short overview of MLlib and Spark ML, which are our two APIs for doing data processing and data science in Spark. And we'll have a whole bunch of hands-on labs for you, with the idea being that we're going to be learning by actually analyzing real data sets. So we're going to get a chance to actually work with ETL. We're going to do some k-means analysis. We're going to work with decision trees, do some cross-validation. We'll also actually call out to legacy libraries such as scikit-learn and see how we can train models in parallel. And lastly, we've got some examples of doing some real exploratory data analysis with Wikipedia. Along the way, we're going to see the use of user-defined functions, various MLlib data types, some plotting with matplotlib. We're going to deal with training and test and validation data sets, sampling, and more. So this sort of gives you an idea of really what we're looking and aiming to do. And I'd like to find out a little bit about you guys. How many of you guys have been working with Spark for at least a month? All right. How many of you guys have been working with data science for at least a month? Excellent. How many of you guys have a preferred programming language of Python? How many of you guys have a preferred programming language of Scala? It's a pretty good division there. So it looked like the Python guys were slightly more in the majority than the Scala guys. So let me ask this question. How many of you guys don't know any Python at all? OK, so a much smaller number. So all of the labs are going to be available for the most part, with one or two exceptions, in both Python and Scala. And I'll just choose one language to lead. So I'll lead in Python, because Python tends to be the most popular language when it comes to data science. Unless, of course, you prefer something like SAS or MATLAB. Or R, for that matter. R being, of course, the last. There you go. So a few hands for R. R being, of course, the third supported language on the Spark ecosystem. And R support is a little bit limited when it comes to Spark. What they really aim to do is to allow you to query and pull data in from Spark using R's DataFrames capability, and then let you use your traditional R tools. So they've basically created an integration from Spark to R, but it's not a first-class, fully supported API the way Python and Scala are. So before I go any further, let's just go over some of the logistics for today. So I've got a second deck here. Oh, yay, Microsoft Office. So I'm traditionally a Windows user, and I switched over to a Mac today because of a projector cable issue. So you'll see me fumble around occasionally on a Mac, but I am resolved that I'm going to become an expert at using Macs and want to switch by the end of today. So first, just a little bit about us, who we are. So we represent DataBricks. DataBricks was founded in about 2013 by the creators of Spark. And we really do, well, this slide's a little bit dated, but about a year ago, we did 75% of the commits on Spark. And since then, that's tapered off simply because the entire ecosystem of Spark has expanded with more and more community adoption. We like to say, Spark, I am your father, which of course is very fitting, being in the Imperial Room. A little bit about me. So I am the training director at DataBricks, and this is Waleed. Waleed is a data scientist. Let me pull up Waleed's bio right here as well. Here you go, Waleed. Walid is a data science. He's been working in the areas of machine learning, natural language processing, etc. Walid, I'm going to let you introduce yourself here.
Basically, all the great stuff Spark is allowing you to do now, I've been doing for a while. But applying that to big data was, a great breakthrough. I do a lot of work helping government customers a lot. But basically, anything that has advanced analytics, that has AI applications, that has machine learning applications is where I'm interested. And having Spark to help you in the background has been a fantastic addition to the tool set. And I'm sure once you know more and more about it, you will realize how important, how great some of the things you can do with it will be. Doug?
Perfect. So with that said, the last thing we want to mention is the agenda for today. So we're going to start out today at 10:45. We'll have a coffee break. I don't have a clock visible within my field of view, so feel free to say, hey, Doug, coffee break time. And we'll take our coffee break. At 12 o'clock, we'll break for lunch. Lunch is provided. And again, at 2:15 and 4 o'clock, we have breaks. There'll be a soda break at 2:15, and at 2:45, we have a coffee break. And let's see here. Get rid of the little pop-up on the screen. So this is what I'm getting used to on the Mac. Now, this slide is very important. I'd like to get everybody to go to this first tiny URL, tinyurl.com/spark-ds-files. Oh, excuse me. Scratch that one. Go to the second URL. My bad. Second URL, Spark Data Science TD1, the second URL here. So what happens when you go to the second URL here, the class notes? This is very important. So you go to class notes here, and this is basically going to be our web page. Let me zoom in a little bit. Whoa, I see everybody's little arrows in. That's pretty cool. Everybody's clicking all over the place. Pretty neat. So you guys have write access to this for a very specific reason. So first of all, notice the class schedule is in here, as well as the list of instructors and TAs. We're going to introduce the TAs here in just a brief moment. Notice as well, this is very important, is the class file share. So any URLs that I post at all during class, I'm going to post to this master document right here. So any code snippets I want to give you, any URLs I want to give you, etc., we're going to post here. So go ahead and click on class file share. I believe you need a command click or control click to get that to come up. How do I click on a URL on a Mac? Is there a secret? Has anybody figured it out? Command click. That's what I thought I was doing. I'm not getting anywhere. You guys getting anywhere? There we go. I could right click on it and copy link. That will work. Open link. Oh, that's the survey. Is that the survey coming up? Or did I just misclick? Open link. Huh, is that coming up for you guys too? Okay, that's okay. You should be getting to a directory that simply has class notes, correct? All right, so my Mac noviceness is showing up at this particular moment, but I will be an expert by the end of the day. I hear Mac is that easy to learn. All right, so any updates I make to the materials, I'm going to upload after class. So if we make any updates, code up any examples, etc., live during class, I will upload them. What you have on your thumb drive, though, is completely up to date. It's just simply a matter of I'll upload everything there online as well. The reason they're not there right now for download is very simple. We don't want everybody hitting the Wi-Fi. Let's say it was just 100 megs, but we have 600 people getting training. We would saturate the Wi-Fi very quickly, and this class depends on the web in order to access our environment. And last but not least, please do not leave without giving us feedback. There is a link to the, we'll be giving you a link to the feedback form for this class. I'll be posting it here. I'll be highlighting it inside of this doc. And it's very important. We value your feedback. The conference asks we get 95%. So if somebody wants to call dibs right now, the rest of you guys have to do the feedback form. Very, very important to us. Now, this is equally as important, getting help. So during class, there's different types of help you may need. If it is related to the event, an emergency happens, you're looking for the bathroom, whatever, there's a door monitor that'll be in the back of the room just outside the door. You can't see them because the door is closed. You can ask them for any directions, where to go, how to get support, etc. If it is related to having trouble logging into the lab environment, and we are about to test the lab environment right now, if you have difficulty logging into the lab environment, you can email training-support@databricks.com. We have a team of engineers who have access to resetting passwords, etc., at your disposal. Everything else comes to here in class. So we've got our TAs. So if you're looking for help completing a lab, contact any of our TAs. TAs, wave your hand in the back of the room. There you go. We have 3 TAs in the back of the room. They're happy to help you complete any of the labs. We've deliberately made the labs challenging with the idea of really having you learn data science on Spark. And last but not least, we have something called the Q&A parking lot. The Q&A parking lot is at the bottom of this file. And the idea here, and this is why you have edit access to this document, the idea here is you can simply append questions at the bottom of this document. If you put your name, which can be a question from anonymous if you'd like, then we can actually associate it with you when you come up and talk to us later. We say, that was your question. And you simply say, for example, question from Doug Bateman. Other people can like your question. Eventually, we'll answer your question. Very low-tech likes. You just type in that you like the question. And our TAs in the back of the room will be curating and saying, hey guys, this is a very popular question. We're going to take the most popular questions and make sure they get answered. We'll be answering other questions offline in the back, while Lee will be answering questions as well as our subject matter expert in the room. Lots of good stuff. Tell us a joke. Let's see here. Anybody want a joke? It's early in the morning. I think it's too early in the morning for a joke. We'll do a joke right after our first stretch break. All right, so with that said, this is the Q&A parking lot. So when does it mean then that you should interrupt the instructor with the question? So number one, make sure if you have Wi-Fi problems, that is, you can't get to your shard or you can't get to the internet at all, let the TA know. If your lab environment starts being flaky, first 2 things to try is refreshing your lab environment, which we're going to log into in a moment. Failing that, check and make sure cnn.com comes up so we can know whether it's an environment issue or an internet issue. Alert the TAs. They have a whole escalation path available to make sure that we get any issues with Wi-Fi resolved quickly. If the font size is too small and you can't see my code example, I'm more than happy to make it larger. I can even do a screen share so that you can see it directly on your monitor if needed. Or if you're getting lost with the main essential point of a slide. So there's going to be a lot of questions that come up going, ooh, this is related to something I want to know more about. Question parking lot. But if it's like, wait a minute, I didn't get this critical idea. Can you clarify? Ask the question right away. So that's it. This is the way we're going to interact with 75 of us in the class, or actually I think it's 100. So those of you who familiar with 100 people, you want to kind of be a little bit careful editing the document in a shared way and be considerate. Hopefully nobody will delete the entire document, etc. So with that said, let's go ahead and log into our lab environment. So we're going to test out our lab environment right now, first thing in class. So what's going to be involved in testing our lab environment? So number one, just click on the link here. Well, you can't click on it, so you're going to go to ssw2016.cloud.databricks.com. That's also written down on the credentials. How many of you guys have already logged in? Ah, so we don't have to spend any time on that. Did anybody have difficulty logging in? Ah, this is excellent. No loss of class time logging in. We love that. So once you're logged into the class environment, you'll see something that looks a bit like this. And you go, well, all right, I'm logged in, but where do I go for now? Where do I go from here? So let me show you how to use your lab environment. Over here on the left is our menu area. Click on Workspace. And you get a little browser of all of your files. And so if you were to come here to Labs, for example, notice that you have access to all of the labs for all of the classes. One of these that's available in here, notice, by the way, data science folders right here. One of the other things that's really worthwhile pointing out is the language guide for those of you who are unfamiliar with either Scala or Python. It's a really nice quick cheat sheet. So for example, I'll pull up the Python guide. And you'll see that it's a really nice, concise overview of how to do some things in Python. And it also tells me I should make my font a little bigger. So let's see here. There we go. Is that font a little bit better? Perfect. So it's a short little language guide. One thing I'm going to do with my language guide right now, oops, except I lost my place, is I'm going to come up here to the top of my language guide. And notice if I hover between cells, there's a little plus sign to introduce a new cell. And then I can just write some code right here. 1 + 1. Now, in order to run this code, I need to actually have a cluster set up. In order to actually run this code, I need to have a cluster. Now, the beauty is when I try to run this code for the very first time, I just press Control-Enter. And it says, you are not yet attached to a cluster. Would you like me to make you one? Now, we're running on what's known as DataBricks Community Edition. And you'll have access to these files after class. You'll be able to import them into your own DataBricks Community Edition later. And it's currently spinning up a cluster. Now, in order to keep costs down, we don't get 10 computer clusters each. That would be really, really cool. But in order to keep costs down, what we're running is a simple local mode cluster, 6 GB of RAM, which would be plenty sufficient for the data analysis we want to do today. But it's very easy to scale that up if we wanted a 100-node cluster, for example. And right now, it's launching a cluster. I can see that my cluster's launching if I come over here to clusters. So there's my cluster. Ooh, terminated due to error. Those are terminated clusters. My other cluster's probably still booting. Let's see how it's doing. So we come back to language guides. There we go, Python guide. And see if it actually evaluates. So it's still coming up. We want everybody to go ahead and launch their clusters now. Go ahead and launch your clusters, run 1 + 1. It will take a little while for the cluster to boot because what it's actually doing is provisioning for you an Amazon EC2 node here. Or actually, it's a Kubernetes instance running in a pool of Amazon EC2 nodes. Question for you.
Yeah, I launched it, it said terminated because the cost was too high.
Did it? OK. TAs, can you go ahead and Slack the channel and say that it's terminated because of the spot prices?
Yeah, we're working on it.
You're working on it?
Engineering's working on it.
Oh, perfect. Thank you. All right, so this is exactly why we test this thing out first thing. So how many of you guys are familiar with Amazon spot prices? Basically, if you get a spot-priced machine on Amazon, they're nice and cheap. But the catch is if there's a surge in demand on Amazon, they raise the price on you and they shut down all your machines. So we are working on that now. Question?
When people change their region to 2A or 2B, so right now everything is 2C, the spike in the spot price, and
Okay, so I go over to the cluster page. So let's go ahead and get everybody to go to the cluster page right here on the left. The clusters page right here on the left. You'll notice a button here called Create Cluster. And under Advanced Settings, we can choose which Amazon region we want to use, and different regions have different areas of the country. And we're able to choose one that's a little bit less busy, so I'm just going to call this My Cluster. I want to run Spark 1.6. Later on, if you guys feel like playing around with the 2.0 preview, you certainly could. We're going to run 1.6 in class today because it is the latest released version of Spark. And then instead of choosing 2C, we can choose, for example, 2A. We just choose Community Optimized. That's the default here. And we create cluster. And there we go. Our cluster should now be coming up. So if it says terminated, you don't have to delete it. Is yours actually active? Yours is pending? This one here, you mean? Okay, go ahead and just give it some time. Let's give it some time. This is exactly why we're testing out our cluster before we get into the very first set of slides. Yes? Yours just terminated on 2A? 2B. Try 2B then. All right, somebody's up and running on 2B. Perfect. So if you wanted to kill one that's currently spinning up, you can terminate it while it's still starting. I'm going to go ahead and do that for mine and start up on 2B. If yours came up, you're good, but you still risk the possibility of the spot price surging again and shutting down your cluster. So when that happens, if it happens, you'll just switch over at that point to 2C. Or 2B, my bad, 2B. And our clusters are spinning up. Now, while those clusters are spinning up, the next thing that we want to do is do a very short overview of what are DataFrames. Does anybody need just another moment to finish clicking and launching? Like, I know that it's going to take a little bit of time to spin up. Right now, CE is busy saying, oh, I've got to scale. I got a whole bunch of new users. And so it's launching new Amazon EC2 instances elastically, which is exactly what we love. How many of you guys do data science and had your manager say, well, how many computers do we need for the cluster? How many computers should we order? And of course, you don't have the computers yet to even write the app to figure out how many computers you're going to need. So this is why we think big data is just married to the cloud. It's just a perfect fit, a match made in heaven. Because you say, you know what? I need 100 computers, but only for the next 2 hours. Why should I pay for 100 computers for a year sitting in a data center chewing up electricity when I can just fire up 100 computers when I need to do a compute job? So that's what we're doing right now. All right, so while we're waiting for those computers to come up, this is why we did this first thing, having Amazon spin up the computers. We're going to talk a little bit about DataFrames. How many of you guys are already familiar with DataFrames and Spark? Oh, I love it. Last class, the numbers were lower. How many of you guys are still doing most of your work with RDDs? Oh, still a significant portion of the class. But let's talk about DataFrames here. So what is a data frame? Very simply. Oh, go away. All right, that is not scaling the way I want it to. So what is a data frame? Very simply, it's tabular data. Now, how many of you guys would like to be able to see these slides on your local computer? Notice they are on your thumb drive under Data Science in a folder called Slides, and it's just index.html. It's written on Reveal.js. So a data frame is basically, it's very similar to what you would think of in terms of tabular data, but what it really is an interface on top of Spark. So notice here what we've got is name and age, and then it looks like some kind of compound data structure, address, which is really just another object, and I could continue dealing with hierarchical nested data if I needed to. I could even read JSON in as data frames. And then I can express my queries in SQL or other technologies. So if you notice with my data frame, and I know this is very hard to see and I'm not able to zoom in. Actually, I can. There's the Mac key sequence to zoom in. What is that? It's Command Option plus. No, Command. I set up the accessibility feature. There we go. Perfect. How did that work? All right. So notice here I even have a schema. Name, age, and address, which is then made up of city and county. So I can deal with hierarchical data as well as flat data. Now, how do I undo the zoom? I remember how I did this. There we go, Command Option. If I forget, Command Option was what I was using. There's zooming in the browser, and then there's zooming on the Mac screen itself. All right, so that's data frames. Now, what does the code look like when it comes to data frames? What does the code look like when it comes to data frames? So here, for example, I've got an object person and an object address. I could go ahead and create these guys essentially as row objects, but keep in mind a row here is really just an object. These are just named tuples in Python, which are a lot like case classes in Scala in the sense that they hold data. And then I could simply say, create for me a data frame out of this array. Now, that's nice, cheap, easy way if I have local data sets. Now, I could also read a data frame from a larger data set off of disk or even from a Parquet file. And then I call display. And after I call display, I get to see my data frame. Oops. So let's take a look at some sample queries with data frames. And why are we taking a moment to do this? Because data frames are central to the Spark ML library. We can build pipelines of machine learning processing on top of data frames. So let's take a look here. How would I query for people whose age is older than 30? So query people where the age is greater than 30. Now this is in Python. If you were using Scala, you just put parentheses there instead. You can optionally use the $ in Scala for those of you who are familiar with it. All right. What about selecting the name of people from the USA? So here, I want people whose country is the USA, and I only want to select their name. This should look familiar with anybody who's worked with pandas. Anybody here worked with pandas? There you go. So this looks extremely familiar. Deliberately done as such. How would I get the average age and do an aggregation function? People.aggregate. I want the average age. So notice I have to import from functions. And then I call average. Question? So how would I do it as a SQL query rather than as a function key? So let's back up a little bit and do an example of that. So let's grab this code example. Let's see if my shard is up. So our cluster is running. No, it's not. Am I logged into Brian's cluster? So let's see here. If I come in, and let's check my clusters again. Create cluster. Advanced settings, 2B, community optimized. Let's give that another opportunity to launch here. Should come up relatively quickly now that everybody else has launched. As soon as that's done, I'll show you an example of running a SQL query. You have two choices. You can actually use the DataFrames API, which is what we've just been seeing, or we can actually run SQL queries. And I have some slides that will describe the SQL query syntax as well. We just have to wait for it to come up. But you can express it either using pandas-like syntax or SQL queries. Now, here's something I want everybody to get while we're waiting for our shards to come up and our clusters to come up. Why DataFrames? How many of you guys love your RDDs again? Oh, fewer hands than said they were using RDDs. So that should tell you something right now. So the idea behind DataFrames, number one, is to make your query syntax much, much easier than your typical MapReduce type code. So it's much easier to represent something in terms of a relational type query with DataFrames. The other thing is it's declarative. Instead of saying how to do a computation, you're really saying what you want. I just want all people who are in the USA and I want their names. And then under the hood is a query optimizer. So rather than you writing a procedural program to query your database, you say what I want, and the Catalyst Query Optimizer, which is a rule-based query optimizer, will go down to disk and actually figure out what it believes is the best way to run this query. And it's got a whole bunch of really advanced features. For example, if it detects that it's going against a relational database over JDBC, it may push some of the where clauses and joins down into the database. Or if it's reading against a Parquet file, it may determine, you know what? I don't need to look at the entire Parquet file. I can look at just these partitions of it and be very, very intelligent. It's the Catalyst Query Optimizer. Now, when it comes to working with DataFrames, there's a few things you want to be aware of. These are your friends. So you've already seen an example of doing filter operations. These correspond to your where clauses. Select operations. This is really just saying, hey, I want to take this row and map it down to this item. You can drop columns, and you can even join data frames together. Now, keep in mind, if I do a where clause, what am I getting back? If I say, give me all the people that are in the USA, what am I getting back? Another data frame. And then I could turn around and say, now, from the people that are in the USA, select their name. What am I getting back? A data frame of names. And then I could say, give me all the names that start with the letter A. Now what's really cool is the Catalyst Query Optimizer will actually do the where clause before the select even to really optimize things. It'll rewrite my query. But notice that all transformations give you another data frame. Now here's what's really remarkable about that, and it's just like working with RDDs. When you run these types of queries and you're getting new data frames, in order for the query optimizer to work, nothing will run until you get to the last stage and you say, show me the result. Show me the result. So I'm building up an entire query here. And I'm going to get the entire query in memory, in the driver, to figure out what's the fastest way to do it before I start any computation at all. So right now, no actual work has been done because I've not asked it to show me the results. The real power then comes when I call an action and I say, how many results are there? Or bring the results back to the driver. Or save the results off to disk as a Parquet file. Those of you who have been working with Spark, which I believe is everybody, are familiar with this lazy architecture, correct? Just out of curiosity, how many people are not familiar with the core Spark? There's a few people, but you're not really raising your hand. So most people in here raised their hand earlier, but this is good. I'm going to make sure I reiterate, though, these really essential core concepts because they're essential to performance. If you're still using RDDs, you're doing things the hard way. Generally speaking, you only need to work with an RDD to get your data into a data frame format. So maybe you've got a text file, you need to parse it up a little bit, get it into structured data, and then from then on, you want to be working with data frames. When you get to Spark 2.0, they're doing something extremely cool. They're unifying a lot of the API between RDDs, data sets, and data frames. Data sets are basically data frames, but they've added back strong typing, which of course the Python people don't care about because Python is a nice dynamically typed language. But the Scala users really wanted their type checking, which was added with the data sets API. So in Spark 2.0, data frames are just a data set of row objects. And then you could say, no, I want this to be a data set of user objects instead. And you can absolutely do that. Very, very powerful. Question here. Yes?
So you don't use data set in Python?
Say again? Oh, you would still use data sets in Spark 2.0 in Python. Just the advantage of it is a little bit less obvious in the sense that what are you getting? Well, instead of a data frame or data set of row, I'm getting a data set of user. But you either go row.firstname or user.firstname. Either way works. But if you have an IDE that gives you some tab completion, there's still some benefits there because it does give you type hints in Python. So no, data frames and data sets will both work in Python and Scala in Spark 2.0. Or even in 1.6, but they've unified it in 2.0. In 2.0, they've even added some RDD type functionality to data sets. Although once you start using things like map and reduce rather than calling data frame type syntax, you lose the benefit of the Catalyst optimizer. We'll talk about these types of things later. I just wanted to give you a background on what are data frames. So for now, is everybody really clear this idea that I can write these SQL queries? So let's take a look and see how my cluster's coming up. Yay, my cluster is up. That is what we wanted. So now I'm going to come over here to Labs, and I'm just going to create a little notebook. Scratch. And let's just grab the example from the slide for the moment. So we're going to just create a simple test data frame for the moment. Come back over here and run my command cell. And there you have it. I've got a data frame in this case of employees. Bob at 35 lives in London. Now, you guys had already seen that I could do queries using the Panda style syntax. So let's go back over here. And select everybody with the name. Come back over to the data frame. Perfect. And now notice what I'm getting back is a data frame containing name, because it's all the people in the USA with the name. but I don't know the contents of it. I won't know the contents of it until I say, show me the result. So if you look here, does it say, notice when I created the data frame, it launched 2 Spark jobs? But down here, it didn't launch any Spark jobs, did it? Because I haven't asked it to show me any results. But now, if I take this, let me just assign it to a frame, df. Now I go df.count. Now it ran a Spark job and says, whoa, there's only one person from the USA. Who is it? I can call dataframe.show. And I see that Sarah is from the USA. But I decide, you know what, that's not pretty enough. Well, I'm running in the DataBricks product, so if I go dataframe.show, or excuse me, display dataframe, it does the same thing, but it outputs it as HTML instead. So if I were to come up here, notice that when it's outputted as HTML, I get a nice little graphical browsing. So if you ever see me use display, that's just simply to make our UI look prettier. But the open source version simply does everything as ASCII art so we can run in the command line terminal. And you have a choice of doing it either way. Now, somebody had asked the question, how do I query a data frame using SQL? And I think that was a really worthwhile question. So how would I query a data frame using SQL? Now, this is a bit tricky. The first thing I got to do if I want to query it using SQL is I've got this object and I need to give it a SQL table name so that I can query it. So I'm going to go people.register temp table. People. Just to make it clear, I'll call it peoples, just so that you can tell that the variable names don't match. And I run it. Now, I can go SQL context .SQL, select star from peoples, and decide I want to display the results. I'll just do .show at first. .show. And notice I can express my query using SQL. Now, if I wanted to be nice pretty, let me zoom in again. If I wanted it to be nice and pretty, I could call what? Display. You guys got it. Learning fast. Display. Now, built into this notebook, I could go a little further. I could even have it easier. I could just say, now this is a notebook feature here with this particular DataBricks notebook. I can go %SQL, select star from peoples. And I get the same thing. So how many of you guys like the SQL style? How many of you guys prefer the pandas style? Interesting. This is the first time I've ever had the pandas style outrank the SQL style 2-to-1. It's purely a matter of choice. Now, I hear this question in your mind. Is one faster than the other? Not at all. Performance is the same because they're both running through the Catalyst Query Optimizer. Now, somebody might say, well, there's a little tiny bit of time required to parse a string. Okay, you got me. There might be a millisecond to parse a string. But in terms of scalability and overall performance, they're going to perform the same. Because they're building a Catalyst optimized query plan underneath the hood. Now let's go back and finish our introduction to data frames here. So we talked about the why. We talked about the idea that nothing happens until you say, show me the result, and that's what makes optimization possible. And so when we actually execute a query for a data frame, what are we talking about when I run a data frame? Well, we're reading the data. The Catalyst Query Optimizer is running under the hood, and generating for us the RDD transformations. So data frames are compiled into RDD commands, transformations and actions. The data frames get turned into underlying RDD operations, and the results get delivered back to us. Whenever you say, show me the result, this is what actually happens. Now, when it comes to performance, this is what I want to get everybody to get when it comes to data frames. Notice, in general, they perform better than RDDs. Now, I hear the obvious question. Didn't you just say that DataFrames gets compiled into RDD code? Yes, it does. But the Catalyst Query Optimizer is able to do what's called whole stage code generation. So it literally generates code on the fly to roll all the work up into the smallest, most concise query plan possible. And you would have to be an extremely good Spark programmer to beat the performance of a data frame. It's not just calling map and filter. It's actually calling map partitions and generating bytecode on the fly to execute this, which is very, very cool. The other thing worth noticing is notice the performance difference between Python and Scala when it comes to RDDs. Well, that's because with RDDs, you're passing these lambda functions around to map and filter, those of you who've worked with RDDs. And that meant that I had to call into Python to run those functions. No such performance hit with data frames. With data frames, I'm just expressing what I want, not how to do it. The Catalyst Query Optimizer decides how to do it, and therefore, notice there's no performance difference between whether I use SQL, R, Python, or Scala. The scalability and performance will be the same. And later when we talk about user-defined functions, we'll find out that's the one exception. If you start calling into Python code with a user-defined function, that's when the performance hit finally comes in, because it has to go to Python to run that function. But otherwise, simple selects, filters, sorts, aggregations, averaging, etc., joins, all the same performance across the languages. Very, very powerful, and we love this. So before I go any further, any questions on what are data frames? Oh, you got me a soda. Thank you so much. They know I need my caffeine because I was up improving slides till 3 o'clock last night, making sure all your labs are going to work. So perfect. Any other questions related to data frames right now? This is a good moment. Say again? Is there any reason I would choose an RDD over a data frame? So I can give you two scenarios where you might choose an RDD over a data frame. The first is you're reading some type of unformatted data source, like a raw text file, that you want to parse and turn into structured data. So maybe you've just read a big text file, and maybe it's not JSON, but some unknown format where there's not a built-in reader, because there's already a built-in JSON reader in the DataFrames API. But let's say it was YAML. And let's say there was not a YAML data frame reader. What you could do is read it in as an RDD, parse it, and turn it into a data frame. So we use data frames to get our RDDs to get our data from whatever raw format into something structured. And then from then on out, you really want to use data frames. What's the other time I might use RDDs? Now, I'm not even going to bother spending a lot of time on RDDs right now because you guys are familiar with Spark in general. We'll see a little bit of RDDs later. What's the other time I might use RDDs? And the answer would be if I really want manual control. So for example, let's say I have 1,000 URLs and I want to go out to a website and download the contents of 1,000 URLs in a parallelized way and grab the JSON files at each of those URLs. Well, I could at that point make an RDD of 1,000 URLs and call map and have the function inside of map download the websites. And so I get a little bit more control about how the partitioning is done. I could even call map partitions and have a bunch of threads pull them all in parallel if I wanted to. So that would be the other exception to the rule. Now, the times you need that are relatively rare. And Spark streaming. So they actually now have Spark streaming data frames. So Spark streaming did not work with data frames, but that has been created. I believe it'll actually be released in Spark 2.0, the streaming data frames. But for now, yes, Spark streaming requires RDDs if you're running on 1.6. All right, so with that said, what we want to do is get into just our first exposure to working with data frames. And we've got a couple of choices on labs when it comes to this. So the lab we're going to go with is called WikiEDA. WikiEDA stands for Exploratory Data Analysis. And I'm going to pull up the Python version. Now notice that there's an answers notebook and a student notebook. The student notebook simply leaves us some nice opportunities to fill in the blank and actually do some learning when it comes to data frames. Now for those who would prefer to simply run the answers, you can use the answers notebook, but my experience is that the learning happens in the hands-on. So we're going to try to maximize as much hands-on as humanly possible. So here's what we've got. We have loaded some Wikipedia data onto a shared drive. And what we want to do is load the data and do some exploratory data analysis using data frames. So step one, I got to read a Parquet file as a data frame. So notice the API here, SQL context.read.parquet, and the path to the Parquet. Now, since I plan to explore this entire data set interactively, it may make sense for me to cache it in memory as much as I can fit into memory. It's going to cache what it can in memory. We'll talk about caching best practices later. In this case, I plan to do exploration of the entire data set. So I'll cache the entire data set. But if I only wanted to explore a subset, it would make sense to only get the subset I'm interested in before I do any caching. So go ahead and run this cell. Open up the student notebook and run that cell. Did I lose? Oh, no, I have to. OK, good. My cluster's up. It just says, notice, this notebook has not been attached to your cluster. So I just say attach to my cluster. I've already got a cluster running. Now I just need to attach to it. And there we go. Notice there are 8,025 lines. So let's take a look at it. So I could just go display. I'm going to add a cell. Remember to do that, you just hover over the plus sign between lines. And you could take a look at the data frame in here. What do you think this is? So all I did is I ran the first cell, and I did this. Hey, Andy, I see you in the back of the room. Could you get us some printer paper so I could make little place cards that they put up on end to signal they're done with the lab? So I need about 100 pieces of paper. How do you run just one cell? Great question. I'm so glad you asked that question. That is you're hitting run all, aren't you? Yeah. All right, how did I run one cell? I'm so glad you asked. I should have mentioned this. Control, even on a Mac, control run. Now you say, how did I know that? Well, right up here, you see this little keyboard? That's the keyboard shortcuts. So notice that Control-Enter will run the cell. Shift-Enter will run the cell and then highlight the next cell. And then Option or Alt-Enter will run the cell and add a new one below. That would be a nice little button there, Run Current Cell. So Andy's in the back of the room, so you can make feature requests to Andy. Run Active Cell, a little button right here called Run, so that you don't have to guess Control-Enter. That's probably a good user interface improvement. But you know, this is based off of IPython Notebook, the idea, the concept of it. So in IPython Notebook, you also ran things with Control-Enter. So Andy is the vice president and founder of DataBricks, and he's sitting in the back of the room, and I'm making him get his printer paper. All right. So now notice if I call display. Was everybody able to run that first cell and load the data set? Perfect. So now, at that point, I call display, and I did this on my own, df.small, and notice what my data set is. It's a last contributor, a redirect, and then text of a Wikipedia article. So this is a Wikipedia article. I can also see the title. And this is a Chateau de, and I don't know how to pronounce that. Chimaranda? Chateau somewhere in France. I look at all these different Wikipedia articles. Now let's take a look at the format of this thing. So we run this little print statement here. Notice if I just print out the data frame, so I just go print in the name of my data frame, we can just do that. Print df small. It gives me the schema a little bit of my data frame. Last contributor is a string. Redirect title is a string. Text is a string. Timestamp is currently represented as a string. I would need to parse it into something else. The title is a string. I could also go df small dot describe. Oops, df small dot, what is it? Print schema, thank you. Print schema. And you can also look at the schema this way, if I zoom in a little bit. And you can see whether a column is considered nullable or not, etc. So this is just a little bit of exploring my data set, because this is a new data set. We hadn't looked at it before. And if we look at what is the type of df small, notice its type is PySpark data frame. There we go, print schema. Now, we can actually make our schema is actually going to be built up of what we call struct types. Let's take a look again. So I go print schema, and notice that each item in my data frame here is really just struct type. That's basically like a row in Python. And so I can read a little bit about struct type if I wanted to by just running this next cell. And notice a struct type is basically just made up of fields. Struct type is made up of structure fields, which is a name, a data type, and some metadata, like whether or not it's nullable. Now, we don't need to get into the guts of it here. We're just looking a little bit at our API, and I say, why? Well, because When I read my schema, remember it read it all as strings initially because that's the format that it was in Parquet. All right, printer papers. We'll need printer papers and pens. Give me one printer paper right now for a demo purpose. And actually, pens we're not going to use. We'll make it big enough. All right. So what I need is a visual signal when I give you a lab to see how fast you're moving along. So what we're going to have you do is take your pieces of paper and let's see here, fold it in half and then half again. These are tiny pieces of paper. We're going to make it work. So you fold it in half. Actually, just fold it in half and then fold it in half a second time, just like this. So half and then half. So it looks like this. Now it's nice and sturdy. And here's the signal. On end means I'm ready to move on. Flat means I'm still doing the lab. Once you're ready to move on, check on your neighbors, see if they need help. The more you help each other, the faster we'll be able to move. And more importantly, if you see your neighbors actually done and they haven't raised their name tag, go, hey, raise your flag here so that we can move on. Because I use this as a way to gauge the sense of the room. Now, if this was a small classroom, I'd have you put your names on here and I'd learn your names. We're going to skip that for today. Because there's no way I could read this small piece of paper from way back up here. But I just folded it once and folded it twice. I told you to do it the long way simply so I can actually see it. We'll see how this works. It's going to tip over a lot, I'm sure. Go ahead and lay them flat for now. Are they falling over? Is it working at all? There we go. You could always, we could do a different style of strategy. Maybe this would work better. On top of your laptop means done. Not on top of your laptop means I'm working. How do you like that? A little better? Let's do that. On top of your laptop, I'm done. Move on. Side of the laptop, I'm working. And of course, the way to get a TA's help is to raise your hand. Okay. So we were just looking at our data frames. We were doing some exploratory data analysis of our Wikipedia data. And the first thing I said I'd like to do would be to change the schema of the data when I read it in. So in this case, notice I want to read in some data that would consist of a couple of rows. I can specify the schema if I would like. I have a field called title, a field called number of edits, and whether or not it's been redacted. And I can say title is a string, number of edits is a number, redacted is true, false. I can specify a schema. And notice what that does is I go create data frame. I give it the data and the schema. And now when it creates the data frame, take a look at it. If we look at the schema that we just created, I want you guys to do this exercise. All you have to do is run them right now. Notice that I've specified a schema for the data that I just read in. Great question. How did the Spark context get created? So you've been working with the command line version or the application version of Spark. So the beauty is in our notebook, Spark context and SQL context have already been created for us in the notebook environment. Those of you who would not be running in a notebook environment or the interactive shell, if you were running outside of the interactive shell, you were running in, say, a Scala program you're executing from the command line, it's no big deal. You'd go var or val Spark context equals, and you have to go create a Spark configuration, and you'd build your Spark context. You can Google this right there on the main Spark website. Same with making the SQL context. Creating the SQL context is not very difficult either. In fact, with Spark context, you can go spark context dot get or create. Where is that? Why is my code complete not working today? Oh, I have to import Spark context first. That's why it's not importing. I have to import the Spark context type. And then SQL context. This is used for DataFrames. Notice in this case, it's actually running on top of Hive. It's using the Hive context under the hood in our notebook environment. The Hive context has slightly more power. Today, we're going to focus more on the data science and less on the Spark 101, so we won't go into detail about setting up your Spark context. But if you were curious, you could always say Spark create Spark context. You go to Google, the great oracle of Google, and you come to initializing Spark. Search for Spark conf. There we go. And initializing, well, that's initializing it in the shell. I don't see it. There it is. New Spark configuration, and then new Spark context with that configuration. So you would just Google for it. The beauty is, because we're working in the shell, we don't have to bog down with that type of minutia. It's all right here for us. So let's go back to our notes here for class and just continue exploring a little bit of DataFrames. Is everybody running these as we go through them? I'm not having you do a whole lot of coding just yet because I just want to make sure I'm recapping DataFrames for you guys. Because we're going to be using these a lot today. All right. Now, take a look at how many columns are in our current data frame. Data frame small. We've got a bunch of columns. Who last contributed? Was this article really a redirect to another article? What's the text of the article? When was it written? What's its title? This is a dump of public data you can download from Wikipedia today. It downloads as XML, but I went ahead and converted it to Parquet for you guys. If you want to see how we downloaded it as XML, there's another notebook called WikiETL, where you'll see us downloading those things. Now, what if I decide, you know what, I don't actually need the text of the article? Drop. Now, this is not dropping a table. This is removing a column. Drop is removing a column. So if I just say, grab the first line of the data frame after dropping the text, notice that I'm getting the last contributor, the redirect, the timestamp. What am I not getting? The text of the article. And I do get the contributor. He's just scrolled off to the side, and the title of the article. Now, notice that that's a row object. I could go in, say, grab the first row, and give me the 0th item. And notice the 0th item is the text of the article. The other thing I could do, because remember, if we scroll up, where was that? There we go. The other thing I could do, now this is, notice working on the original data frame. You guys are going, wait a minute, didn't we just drop the article? That was making a new data frame. If we come back to the original data frame, notice the text is still there. Every time you call a transformation, you're making a new data frame. You're not deleting the old one. So I can still access the text. I've selected the text and grabbing it right there, raw. I could even name the cell if I wanted to, text. There it is. Yes?
So the RDD or the data frame when you drop the column X, is that still somewhere in memory, or is it just printed out?
Great question. Is the RDD still in memory once I created it, dropped it? Remember, nothing actually gets created in memory until you say, show me the result. And unless you cache it, the memory is immediately released thereafter. Immediately. So the only way to prevent the memory from being released was to cache the result. Even if I did this, watch this. So if I were to go, let's add a second cell here. df text equals df small dot drop text. Boy, that ran in 0.04 seconds. Why? Because nothing ran. It's just transforming a data frame. Nothing runs until you say, show me the result. So we come back here, df text. Now notice it kicked off a Spark job, and it happened to be a really fast Spark job because it's only grabbing the first item. So let's grab all the items, or better not grab all of them. Let's just grab 2,000 items. All right, that was still a little bit fast. That took 14 seconds. All right, let's grab 10,000 items. See if I can make it take a little bit longer. 20.24 seconds. Okay. Now, notice though, it's actually not caching df text at all. What's been cached was the original data frame, way up at the top where we called cache. Where is that? .cache. The original data frame has been cached. And so if we were to go and look at the execution model, let's take a look here. If I scroll down to where I called, it's a little hard with me being zoomed in. There we go, df text, take. And we look at the execution of this job. And let's just look at the RDDs under the hood for a moment. So how do I make this full screen? What was the shortcut for full screen on this again? I want to get this in full screen. Do I have to go up to the top? No, this panel. That's fine. I'll do it the old-fashioned way. Attach, view Spark UI. Come over here to jobs. Go to my latest job. And say DAG visualization. Now this is looking at the underlying RDDs. So I can actually go under the hood. Right now I'm looking at the underlying RDDs. And notice something. The green dot means this was cached. Everything below the green dot had to get run when I reran it. So it recomputed those parts, including the map operation, to convert it down into a table. So let's go back again to this guy. And this time around, I'm going to say df text, drop text, and cache it. And I'm going to do an action to trigger actual processing. And now I'm going to come back over to my Spark UI and look at my jobs again. And we look at, in this case, the DAG visualizer for my latest command. That should not have needed to do a shuffle. Did I do something wrong? Am I looking at the wrong job? Jobs. Oh, it's because I did the drop text and then I cached. Okay. But I come in. Notice here, it's actually doing a little bit of extra sorting work, which is annoying. But here, you'll see the original cache data. Oops, back. The original cache data, and then the newly cached data. So it's actually caching further down. I'm not going to go into the details of what happened here. We'd have to go into the actual SQL plan and see. There's a SQL tab where you can actually look at the logical plan for how these things are happening. And one of the things that typically confuses people is, what is this tungsten? How many of you guys have wondered what is tungsten when you looked at this UI? Nobody else wondered? Tungsten is native memory. This is the coolest part of why DataFrames outperform RDDs. With an RDD, it's a blob. You do maps, you do filters, but it's a blob of Java object. With DataFrames, it's structured data. And because it's structured data, the underlying query optimizer is able to generate native memory. And structured in native memory in a way that is much more efficient and takes a lot less memory and can be read much faster. And then they do whole stage code generation, generating bytecode that can read that native memory, which is really just native memory mapped buffers, and read it extremely efficiently compared to actually having to marshal around Java objects. Very, very fast. That's tungsten. We don't need to go into the details there. For now, the goal that I want to focus on is purely what's happening with DataFrames and answering your question. It's only cached if you tell it to cache.
So I have a follow-up. So right now when you're talking about optimizers, you're talking about the tungsten optimizer or the catalyst?
So there's the catalyst optimizer, which rewrites the queries and generates all of the code, including the code that works with the underlying tungsten optimizations. So the Catalyst Optimizer existed for a very long time. Tungsten was a follow-on project to make it use native memory very efficiently. And if you get down to the engineers, they'd be like, we call this part tungsten and this part catalyst. What you need to hear is fast. And that's all you need to hear. I got a few engineers in the room, so they'll be happy to tell you exactly what they consider tungsten versus Catalyst. Tungsten's the memory management. Catalyst is the actual query planner. All right, so with that said, we've done a little bit of exploratory data analysis. Let's get started here. So scroll down to where it said, we've got our first record, and we want to look at it. And notice we can start doing some interesting queries. For example, I would like to select the redirect title is not null and call that has redirect. Now, those of you who prefer SQL, this is not that hard. If you preferred SQL, just for the handful of you who like SQL, I'd go df small dot register temp table small. And then I could go SQL context.SQL select redirect title as has redirect where redirect title not null dot count. Oh, I forgot the group by. Say again? Oh, not full. There you go, not null. I think it was off by one key on the keyboard. So I could write this as SQL, or I could write this as a data frame, and then I could continue group by has redirect. Now I actually want to select this from small, but I actually want to grab, it's only selecting this column. All right, that's kind of boring. But then we want to do a count. So let's do count has redirect. That's very silly. Oh. Select redirect title from small, comma, redirect, my bad, title is not null, as has redirect. I rewrote this wrong because it's a select statement here. Perfect. And then we want to count how many have redirects and how many do not. So let's zoom out again. How many have redirects and how many do not? So we're going to group by whether it has a redirect. And now we're going to select count has redirect. Say again? My select function is wrong? Oh, misspelled set select. So you could write this, and I'm just having a little trouble with my inline view here. Anybody see what's wrong with my inline view? Say again?
You need to actually do where it's from. You need that if parameter starting there. You need to print it in one place. And then delete it. It's like a parameter. Alias. No, outside the print. And then you delete that one parentheses between select and redirect. You don't need that one. Delete that one and the one after has redirect.
From small. There we go. And now I could say show. And how many files have a and I probably want to actually select has redirect as well. And I want to redirect the alias as has redirect. So I could write this in SQL. There we go. How many have a redirect? How many do not? I could write it in SQL, or I could use the nice DataFrames API. I want to select has redirect is not null, group by has redirect, and do a count. I may have been able to write my SQL statement a little bit more concisely. But notice I can do it in either SQL or in the DataFrames API. All right, so we're just exploring our data, doing a little bit of exploratory data analysis. So what I'd like to let you do is keep going a little bit in here and try out a little bit more on your own. So the rest of this article here, we're going to start using some of the built-in functions. So we're going to actually parse a date. We're going to do a little bit of a date format, etc. But I wanted to give you kind of an idea. You can even use regular expressions to start parsing it. But I want you to work through this exercise on your own right now and explore the Wikipedia data the way you would if you were a data science. So reach over, pull out your data scientist hat and say, I want to look to start extracting trends, but before I can, I just want to figure out some big picture information about my data. Go ahead now and complete this lab. The TAs and I and MLlib will all be going around and helping you out. I just wanted to walk you through the early parts. Say again? Oh, you wanted my fancy select statement. Okay. Where was it? I think we could have written my select statement a little easier, actually. I just chose to use an inline view. Pretty sure we didn't need to use an inline view, all things considered.
Doesn't matter, right? Because it's compiled into a simplified query anyway, right? Because I tried both your query and the inline view, and it gave the same query plan.
Say again?
I'm saying it doesn't actually matter if you use inline view or not, because it's compiled to the same job anyway.
That's right. It doesn't matter whether I use the inline view or not. The compiler is going to rewrite it and optimize it in a heavy way. I was just curious if I could have written this a bit more simply. But for those who wanted to see the zoom in, there it is. As we get to the more challenging parts of this lab, I'll probably regroup us here in just a few minutes to do some of it together. For example, we haven't really talked about using some of the ML tokenizer features for regular expressions. So I will show using a regular expression tokenizer. How many of you guys have gotten that far? OK. So I'm going to give it exactly 2 minutes, and then we'll move on to that part. Oh, it's 10:45. When is the coffee break? 10:45. 10:45, and it's 10:45 right now, correct?
2 minutes.
2 minutes? All right, so we will resume by going over some of the other parts, especially the regular expressions part. Some people are trying to do regular expressions the harder way, which would be using RDDs and doing maps and then converting back into a data frame. Perfectly appropriate. Other people are doing user-defined functions to call their regular expressions. After this, we're going to show you a really cool feature called a transformer that can transform items of a data frame into regular expressions, and it's part of our ML pipelines, and that'll be covered right after our break. Go ahead and declare lab plus break. We are going to resume at, is this clock an actual clock? I don't think it is. Is there?
It's 11:44.
11:44.
No, it's actually 10:44. Off by an hour. It's 10:44.
10:44. You know what? I have a phone in my pocket. What am I thinking? There we go. 10:44. We're going to start up at 11. Keep going. I just wanted to make sure everybody got a chance to work with Core Spark right now up until this, and now we're going to dive deeper into data frames. More and more data analysis as the day goes on. All right, welcome back, everybody. Let's see. Is the mic on? Volume on? Perfect. Welcome back, everybody. So did everybody get coffee? Caffeinated up? Got their caffeine drip? I can't tell. It was maybe it hasn't kicked in yet. All right. So we're going to do just a couple of questions and answer. I'm going to pick some of the most popular ones. Then we're going to do the rest of the solution. And then we're going to get into doing some machine learning predictions and doing some data science predictions. But doing the data frames is extremely important because data frames is what you're going to be using to do a lot of your ETL and a lot of your exploratory data analysis. Data frames are the data scientist's best friend. Mastery of data frames is essential for doing your job. So this is why we started with data frames directly. Now, there are a couple of really interesting questions that people asked. The first one is, where can I find slides? Answer. Now, you can find the slides or on the thumb drive. After class, I will also post them to the file share. And you guys remember how to get to the file share, right? You go to, let's see here, well, it's this document. You go to the class notes document, and you see a note here called class file share. There we go, finally. I can get to the class file share. And right now, it's pretty blank. It's just got my intro slides, and that's it. But after class, I will upload a zip file of everything. It's just a very strategic choice to not upload a huge PowerPoint, or it's not even that huge, really. But even a 100 megabyte PowerPoint with a lot of people saturates the downloads. And we want to just, because we absolutely need the internet for you guys to be doing your labs, we're going to give you those slides online afterwards. But everything is on your thumb drives. A few other really interesting questions that I thought I would field here. Coming down. How long are these labs going to be available to you after class? Terrific question. And the answer to that one is also relatively straightforward. So these labs, you can download. I'll show you how to download them after class. And you will be able to make, starting tomorrow, your own account on DataBricks Community Edition where you can upload all of this content. We'll walk you through that towards the end of the day, but I'll go ahead and give you a sneak preview. So if I was here in data science, I could click, or better yet under labs, export as a DataBricks archive, or as HTML zip file. And then, when you import it later on, which is just a matter of right-clicking and saying import, you'll notice this folder here called Setup After Class. And this file, Setup After Class, walks you through how to mount your data sets and how to load the libraries that we make use of. So there's a few libraries that we'll see later on that help do test cases to make sure that you are actually succeeding in your labs. It says, if you did the previous step right, this test assert will pass. So you need a library for that, and that's the README and the datasets mount. Walk you through that, and then if you need more guidance on how to import libraries, we imported this one from our documentation on how to import libraries. But you just start with this README. It says export the lab folders, install the libraries that you require. It tells you where to find them, etc. So it's really straightforward. And datasets mounting, similarly, tells you how to mount your dataset buckets on Amazon S3. So the other question that was interesting is some people said, hey, can I use this in other notebooks like Zeppelin or Jupyter or whatnot, or in my own versions of Spark? And you absolutely can. The one things that you need to be aware of if you were using your own environment, because you absolutely can, this is just Spark code. This is totally Spark code with one exception. Whenever we call display, right? When we called display, I did nice, pretty formatted HTML, so you would just change that to call show so that it showed up as ASCII art. Well, you would just add the test function, test library, to your class path, wherever environment you were working in. And then last but not least, these mount points, you'd have to make sure are mounted and available in your folder area. So you would have to just make sure you've pointed something towards those S3 buckets. And you could actually just directly point to an S3 bucket if you wanted to in Spark. So all of this stuff will work offline. My suggestion is, for the purposes of this class, you'll just move it to your own CE account and run it from there. That would be my suggestion. And your current account will be up for at least a month, probably longer. At some point, we want to shut them down because the passwords are insanely guessable. Everybody here has the same password. We did that for very strategic reasons. We didn't want to have to deal with 20 minutes of people logging in. That's just lost class time. All right, and let's see here. Any other really interesting questions? Tell us a joke. Will do. 2 people liked it. Is the Spark data frame the same as a Pandas data frame? Not exactly the same, but I have a gift for you. DF, where is my cell? All right, I'll just make a new cell here. People dot 2 pandas. Now it's a Pandas data frame. So you could take a Spark data frame and mix it with the Pandas data frame, and then there's some actually really good Python libraries that can link Pandas data frames to Matplotlib. So yes, you can get to a Pandas-style data frame. Question for you.
Only if it's small.
Yes, only if it's small enough. There are some limits in that regard. Did you want to add something there?
Oh, no, yeah. Don't do a 2 terabytes. That's not going to work.
It's subject to memory limitations, not in the cluster, but in your driver. When you called 2 Pandas data frames, notice what happened here. It launched a Spark job. So what it's literally doing is grabbing the data from the entire distributed architecture and pulling it back into the driver as a pandas data frame, so that you can start doing work on it with your traditional scikit-learn and other libraries. Very similar for those of you who are doing R. You can run queries, and then at some point you're going to bring it into memory in the driver so that you can start doing your old R libraries. So there is a lot of support for these legacy technologies. What you're giving up is the distributed computation at that point. And let's see, were there any other questions that stood out? We will be answering these questions here inside of the notebooks. So somebody asked, can you give me a basic example of how RDDs are different than DataFrames? I think this is a worthwhile example. So let me just very, very quickly explain RDDs versus DataFrames. So an RDD. We have an RDD up above in which one? I think it was the earlier example. I'm not used to the Mac scroll. There we go. Which example was that? That was Scratch. Perfect. So what we could do here is make an RDD. So this made a data frame, but let's make an RDD. So I have a copy this code. So RDD is an older API that's much closer to the bare metal. All right, so what an RDD lets you do is it's basically you could think of an RDD as this is a very loose description, a big in-memory or not even necessarily in-memory, a big partitioned array of data. Now initially, that data may be on disk. That data may be out there that you're going to download or on some file, or in my case, I just created an array in memory locally on the driver, and I split it up across all of the machines in my cluster. Now, when you're working with RDDs, you don't get the benefit, you do not get the benefit of SQL at all. So if I wanted to, for example, take a look at only employees who are age 30 or greater, I'd actually have to do functional programming. I'd say I want to filter, given a person, return true if person.age is greater than 30. Now this is not a SQL expression or a pandas expression. This is actually Python code. And it's going to run that Python code. Now, when I do this, notice it ran really, really fast. Why? Because nothing's actually been run yet, not until I say, give me the result. So rdd.take, I'll take up to 10. There'll only be 2. And there it is. I get Bob and Susan. But I'm now working with Python objects and running functions that run in Python rather than working in a declarative language like SQL or Pandas-style data frames. So rather than allowing the system to do a query for me, I'm literally doing functional programming filtering my data. So I could have a little fun. I could come in here and say, let's filter for everybody's age, and then given a person, Give me the person's name. And let's make it to uppercase. And what am I doing wrong here? That should be working just fine. Oh, I forgot a slash. Thank you. All right, and now I could call take 10. I should have gotten some results. Age is greater than 30. They must not have a name column. What was it called? It was called name. That should have worked. Oh, I'm assigning it to a result. That's why. There we go. Bob and Susan. So RDDs are much lower API. It's very similar to DataFrames in the sense you're working with data. The difference is instead of doing declarative programming, you're doing functional procedural type programming. And as a consequence, the system can do a lot less work for you. It doesn't understand what you're trying to do. It's a total black box understanding Python code. It doesn't know how to optimize the Python code because it's raw source code. You could do anything you can do in Python, you could do in a data frame here. But the system treats it like a black box, whereas with data frames, it's able to say, oh, you're doing a filter, you're doing a join, you're doing a select. Let me rewrite this in the most efficient way possible because it's got more insight as to what's happening. So RDDs turn out to be a very painful way to program. How many of you guys have been working with RDDs? How many of you guys found them somewhat painful to do complex things like joins and groups? Exactly. Actually doing rather sophisticated work with RDDs is rather tedious in troubleshooting. So we're not even going to waste class time on RDDs today. We're going to assume if you've worked with Spark, you've gotten the 101 on RDDs, we're going to focus on the data science angle, but this was worth mentioning. The other thing worth mentioning, though, is that given a data frame, I can turn it into an RDD. Yes, RDDs are used under the covers in data frames, but they're RDDs of tungsten direct I/O memory buffers. So you get all this performance, but it's still using the underlying RDD. RDD is the cornerstone of Spark in the sense that what it says is if a machine goes down and you lost the data, it knows how to recreate it on another machine. So it's a resilient distributed data set. So that is the core engine of Spark. The problem is it's a very hard to use API. So built on top of RDDs, we have data frames and data sets and other APIs. And you guys are going to work with those. I will show you a little bit of RDD programming today. You will get to play with some RDDs. But I wanted to make sure everybody knows about data frames because what we're finding is people are still using RDDs on their projects when they really should be moving to data frames as fast as possible. And you should be moving to Spark 2.0 as soon as it's released because it is that much better of an API. Now, of course, if you're like a month away from shipping, I wouldn't do a big change of a version. But other than that, new work, you should be moving to Spark 2.0. All right, so with that said, let's wrap up this lab here. So we got a chance, we got to go through. I think most of you guys had a chance to look at all the columns, do some queries, etc. Then we got a section where you got to play with some helpful functions, right? So how many of you guys got a chance to look at what are all the built-in functions? Now, my personal style is I like to import it as fn instead of func. Just fn for function. That's my personal coding style. But it doesn't matter whether you call it func or function. Notice there's a bunch of built-in data types here. So there's actually quite a bit more into that package than I thought there was in the func. Oh, it's not showing them all. I have to scroll. But why don't we just go to the documentation? So I'm going to go out to the DataBricks documentation at Apache Spark. So spark.apache.org/docs/latest. and I come over here to API docs Python. Go ahead and do that now. spark.apache.org/docs/latest and pull up the docs for Python. I like to bookmark that documentation so I can get to it quickly. Now, once I've gotten to the Python documentation, remember, so I went to Spark's docs latest, I bookmark this, and then I come to API docs and I go to Python. And here I'm going to find pyspark.sql.functions. And there's a bunch of really useful built-in functions. For example, functions to do math, tangent, cotangent, base 64 encoding, ceilings, cosines. Here we go, my favorite, date formatting. Converts a date to the value of so you can basically it takes a timestamp and prints it out as a date. There's a few other ones as well where you can go from date to timestamp. This is going the other way around, from a timestamp to a date, which is really, really nice. You can do some really cool things with date formats. Get the day of month, day of year, etc. Really powerful functions. So before you go making your own, take a look at those built-in ones. And the challenge in our exercise here was to try to use some of these. So here's a really nice feature in this particular one where we said I want to select the timestamp column and I want to parse it into a timestamp. So I'm going to take the timestamp column and parse it as month, day, year, and I'm going to alias that as a date. And this is really, really slick here. Oops, except I haven't run the earlier filtered. Where was filtered made? Here we go. Oh, I got to rerun my whole notebook. And so notice that I take this timestamp type and I can actually convert it into a nice, beautiful formatted date. So in this case, I'm taking a timestamp object and turning it into a date. I can also add additional columns. This is a really useful function in the DataFrames API that I highly recommend you guys look at with column. All it does is add an additional column to your data frame. So take a look now. When I say with column date, I now have a date column. Beautiful. It's the same as doing a select statement to add a column. Just appends a column. And I think you guys got through all of those, and where you got stuck, if I recall, you had no trouble getting things to lowercase using the functions API. How many of you guys got this far? Majority of you guys. So notice you can go to lowercase. You can drop columns. You can rename columns. I should have just had some of you guys run the answers, I think, from this one, because I didn't want to spend a huge amount of time on this lab. But this is where I wanted to get interesting. There are some other nice tools out there. And we're going to learn these from the world of machine learning. So we're going to talk about what are transformers in just a little bit. But here's a nice early preview. We had a string and we wanted to break it up. We wanted to take the text and we wanted to split it up into words. Now, those of you who knew RDDs, you could have gone df small, convert it to an RDD, called map and said, given a row, give me the row's text and split it up by white space. And boom, you've now split up the article by word. You could have done that. And now that was using old style RDD programming. Yuck. How many of you guys did that for that part of the lab? 2 of you guys, okay. How many of you guys wrote a UDF? No. How many of you guys go, I'm not sure how to do this one? Hey, how many hands are broken? How many people didn't get this far? How many of you guys already solved it or ran the answer? There we go. Okay, I'm trying to figure it out. So in any case, we can actually, with DataFrames API, machine learning works directly with the DataFrames API, the Spark ML package. So we can use, for example, the regular expression tokenizer, and let me show you what this guy does. What you say is transform, and you give it the data frame, and it spits out a new data frame. And take a look at it, words df, and let's just call display. Now notice, next to text, hey, oh, words df, tokenizer, transform, parsed, output column words. Where's my column called words? Oh, I see. There it is. There's my column called words. Look at all those words in there. It's a list of words that were found in my Wikipedia article. Now this is very, very typical of doing machine learning and other types of transformations because you have to extract your features. In any kind of machine learning pipeline, you're trying to extract features. So what if we wanted to do word count? We can tokenize our input, preparing to do word count. And notice all it did is append to my data frame another column. All it did was append to my data frame another column. Let me see if I can scroll to the right a bit. There we go. Another column called words. We scroll back up again. Notice output column will be called words. Really powerful way of transformation. We're going to dig deeper into that right now. So without any further delay, what I'd like to do is to get into the machine learning. We could spend more time on this notebook, but I know that you're itching to do some actual, let's build a model before lunch. And so I'm eager to get you there as well. So I have a short set of slides to introduce you to the idea, and then Waleed is going to take you through the first lab. And just because some of you guys, we had a good chunk of the audience who wanted Python, Waleed, are you going to choose Python or Scala? I'm sorry, Scala for yours, right? You said. So Waleed will switch us over to Scala. You guys are welcome to do your lab in Python or Scala. I'll be walking around. But we're going to share the wealth in terms of which language we show on our slides. Now, coming back over to here. MLlib and ML. To transition, we need a joke. So let's see here. An engineer dies, and he goes up to heaven. And he's at the gates of heaven, and the angel's looking, pulls out his tablet. Sorry, Waleed, but I don't see your name on the list. And he points over to a long spiral staircase down. Waleed hangs his head and starts walking. 1 minute he's walking, 2 minutes he's walking, 4 minutes, 4 hours that is. He's walking. He says, my God, don't these people know what elevators are? 8 hours later, he finally makes it down to hell. And he goes over to the demon handing out housing assignments, and the demon says, oh, Waleed, you've been assigned to Fire Pit 22. That's a 35-mile walk in that direction. Get hoofing. Oh, Waleed's like, my God, don't these people know what transportation is? He gets to his fire pit, and it is hot. Waleed's like, don't these people know what air conditioning is? And then it hits him. He's an engineer. So he just starts building improvements. One day God calls down, hey, devil, how's life down there in hell? Is it hot? Devil's like, no, this place is a paradise. God's like, I don't understand. Devil says, well, see, we got this engineer now. He's been building his elevators, escalators, air conditioning, transportation. God, we even have water parks. You really should come down and pay us a visit. God says, what? You have an engineer? That's a mistake. Send Waleed back. Devil's like, no. We like Waleed. We're keeping him. God says, send Waleed back or I'll sue. Devil just scoffs. And where do you expect to find a lawyer? Of course, this is being recorded, so no offenses to lawyers intended anywhere in the world. Please don't sue us. There you have it, though. All engineers go to heaven, and all lawyers, I'll let them figure it out. Okay, did that get everybody's attention back? Remember, the rule of jokes is to get your mind out of the web. When I tell jokes, it's to get your mind out of email, out of web, because I know it just naturally happens, to get you present to the next activity. I'm going to do a few of these slides here, Waleed, and then lead you into the lab here.
Sounds good.
So first of all, Spark's got a good machine learning library called MLlib. Now, MLlib was originally made as a project at Berkeley, got rolled into Spark, and it was made a very long time ago, so it was originally written with RDDs in mind. And the API has been drastically improved since then. But it includes a lot of common machine learning algorithms written in such a way that they can scale. So many of you guys are used to working with local things like scikit-learn that could simply say, oh, I'm going to do the closed form solution for doing linear regression. I'll just invert this matrix here and do linear regression. Well, inverting a matrix does not scale. It's n cubed the size of your matrix. So these algorithms have been written to be highly scalable. In fact, the linear regression algorithm works with something called gradient descent, because you're just trying to minimize error. Error is going to be a nice little parabola, and it's just moving down the parabola to find the minimum spot. And so it scales much, much better with very large data sets, up to billions of rows and millions of features. Highly, highly scalable. But we can do classification, that is spam or not spam, interesting, uninteresting, red, green, or blue. You can have an arbitrary number of classes. Regression, this is where you're trying to fit to an actual number. Like there's a 50% chance this is interesting. Or I predict the temperature tomorrow will be 100 degrees in Walnut Creek, about 75 degrees here in San Francisco. Clustering. Clustering, we have a bunch of data. Maybe they're the voting districts here in California. Or better yet, population centers in California. And you say, I want to group the population centers up into 50 congressional districts in such a way that they clump the best. That is to say, all the things are closest, you find the center, and everything should be closest to the center as possible. Clumping. Another way of describing it is, let's say I had a bird cage. And on one side of the bird cage, I got a water. Another side of the bird cage, I might have food. Another side of the bird cage, there might be a perch for the bird. But I take out all the stuff from the bird cage, the water, the food, whatnot, and I just give you the bottom of the bird cage. And I ask you to tell me, where does the bird generally tend to spend its time? How are you going to figure that out? Well, you're going to look at the droppings at the bottom of the cage, and you're going to see a clustering of droppings over by the water, a cluster of dropping over by the food, and a big cluster of dropping over by the perch. And so you could literally learn, just by looking at groups of points, interesting behavior about a bird. We could be looking at the stock market and say which stocks tend to go up together and down together all the time. And then you need to know nothing. You just look at whether they go up and down together, and all of a sudden you go, oh, these are oil stocks. These are tech stocks. These are small cap stocks. And you can discover these natural groupings without having to have any knowledge about the data, just by looking at how things naturally group. You don't need any domain expertise. That's clustering. Collaborative filtering. You do this when you're trying to pick shows you like on Netflix. So Netflix says, you tend to like a lot of sci-fi. Other people who tend to like a lot of sci-fi also liked these other shows. So we can do a nice alternating least squares type algorithm for a recommender system. And then dimensionality reduction. So one of the curses of machine learning is having too many features. Millions of features. So those of you who are familiar, there's a lot of techniques for reducing them. Singular vector decomposition, eigenvector decomposition, etc. Singular vector decomposition scales much better because you don't have to convert the entire covariance matrix. But all of those capabilities exist as well. If you don't know what I mean by singular vector decomposition, I wouldn't worry about it today. It's a good one to read. Now, there's two packages that come with Spark, Spark.ml and Spark.MLlib. Spark.MLlib is the original, and it's written on RDDs. And you're going to get to do some of that today. Spark.ml has really been a wrapper around that to allow it to work with DataFrames, which creates much easier machine learning pipelines. They'll look a lot like what you would see in something like scikit-learn. So you want to use Spark.ml. And in fact, some of the newer algorithms are being written SparkML native, using DataFrames from the ground up. Some of them are simply backporting into Spark.MLlib for now. So just think MLlib old, Spark.ml cool. But I just wanted to make sure we got over the vocabulary hump. So we're going to be using DataFrames so that we can use our DataFrames as inputs. And the benefits that we get with that is we can store it in many different types of technologies. It displays really easy. And at each stage in our processing, we're just adding columns to a data frame, like we did with Word. We transferred the text into a list of words by adding another column to the data frame. So data frames are a very natural way to be working with our data. So earlier, we actually saw the very first type of object when it came to data frames. I'm actually going to borrow a different slide deck just very briefly to really introduce something with data frames. I'm going to open up a slightly different slide deck because it's got a really good graphical picture of data frames. You'll have to wait for the interesting shot in a minute. This is the wrong slide deck. That's not the one I wanted. Cancel. There we go. Machine learning overview. That's the one I want. I'm going to give you a little bit of vocabulary right out of this slide deck here. So So we already talked about Spark.MLlib being the older API using RDDs. By the way, this is a good example of how we have that file share. I'll put these slides into the file share. And then Spark.ML that uses this newer pipelines API, and it's no longer experimental. So that slide where it says it's experimental is dated. This is now a core piece of the product. So let's take a look really at a nice, interesting example to introduce this vocabulary, because I think it really, really helps. So imagine here we've got a log file, and our goal is to predict how important a log message is for an engineer to investigate. So this particular log file, it's just a normal warning. It says, I've got some jar in my class path, completely uninteresting. This log file, on the other hand, says aliens are attacking the hardware. This is clearly a very important log file to look at because we clearly do not want aliens from Mars attacking our hardware. So this is an example of log prioritization. So we start out, we've got our original data. We call this our instance data. We haven't even featureized it yet. This is our instance data. And over here on the right, we have our label. This is what we're trying to predict. And machine learning is all about finding a model that we're going to use to learn which log files are interesting and which ones aren't. Google uses this to learn what's spam and what isn't. Google uses this to learn which emails you read and mark important and which ones you don't. And machine learning is as simple as a function mapping the instance data to the output prediction value. Now, the art of machine learning is what we call featureization. So we're going to have libraries that we're going to be learning today to do featureization. So number one library here, we're going to do word count. We're going to count. This is one way of extracting information about my log lines. How many times in this line did I see the word running, test, Spark, and aliens? And I could represent this as a mathematical sparse vector. If I was using MLlib, that in fact would be MLlib.linearalgebra.vector. And that could be stored in my data frame. So with linear regression, what I want to do is learn how important different words are. And I could use a variety of strategies, term frequency versus how often the term appears in the entire document, inverse document frequency. But fundamentally what I'm doing is learning which words are important and which words aren't. I'm trying to learn the weights to assign to these words. So I'm going to say the word running, uninteresting. The word test, yeah, okay, that one's interesting. The word Spark occurs so much in my log file, I'm going to give that a negative weight. The word aliens, I will weight at 2.1. Actually, I would have weighted that at 100. It's a pretty important word. But we're going to learn from our data what those weights should be. And this is machine learning. So people who are not familiar with machine learning often go, hey, is this like AI? No, it's just a matter of simple prediction. Question? Say again? That is transpose. I'm doing a, so what's the superscript T? This is W transposed times X, so it's a dot product. Yes. And then I add it all up, and I get the result. So it's all about choosing the right weights, which is machine learning. So how do we do this? Well, the first thing we've got to do is extract features. So we're going to do word counts, and we want to predict those labels. And in the old MLlib, we used RDDs of label points. So when we deal with MLlib later, you'll see RDD of data label points. Later on, you're going to see us using DataFrames instead. So what would your workflow be? Well, you've got your training data. Oh, I haven't installed the fonts on this Mac. That's why they look ugly. I'll install fonts over break. This is a loaner Mac. So ignore the poor-looking fonts, but we'll keep going here. I apply then a linear regression algorithm, and I train a model. Once I've got that model trained, I can evaluate it based on some test data and figure out how well it's done the predictions. Now here's what's really important on this slide. This is what I want you to see. So far in this slide, we've been using the older MLlib terminology with RDDs. Starting with Spark.ml, my data is going to just be a data frame. Not an RDD of labeled points, but a data frame. When I go to do these transformations, or when I go to train a model, I should say, when I go to train a model, I'm going to use an estimator. It estimates the best fit model, using linear regression in this case. But it could have used logistic regression or any other strategy. We call these estimators. Once I've got my model, I can take my model and pipe a bunch of data through it and get the priorities out on the other side. So anything that can take data and make some change to the data, we're going to call a transformer. So notice that my model is transforming my input data to the predictions. You guys, I'll get to your question in 1 second. Notice my model is transferring input data to predictions. Now, let's go back to the lab that you guys just did, because we're going to get to the next lab. We go back to the lab you guys just did. Notice here we used a regular expression tokenizer. What did it do? Took input data, did some kind of transformation to it, and instead of producing predictions in this case, it produced word counts. But so there's three vocabulary words I want you to get. Transformers take data, do some kind of stateless transformation, and produce a result. Whether that result is tokenizing words or applying a model to make predictions. So that's transformers. Estimators, they actually train a model. So they produce state. They're training a model. And of course, the model itself is that learned data, and it happens to be that model extends transformer, because you can transform things, input data into predictions with a model. So this is the vocabulary that we're going to need for the rest of the day. So this is why I went back and did these slides. So let's go back to our slides for today. Where do they go? There we go. A transformer takes in a data frame, spits out another data frame, period. Whether the data frame is breaking up words or making predictions. So it's got a method on it called transform. We could do lots of things with it. We can do logistic regression modeling. We could hash the term frequency. We could do regular expressions, word counting, etc. That's a transformer. And the other one is the estimator. An estimator takes a data frame and produces a model, which implements the transformer interface. So estimators, you say, given this data, give me the best fit. And you're going to see this in our coding as well. So random forest classifiers, linear regression, logistic regression, cross-validation, all of these are going to give me best fit models. Inverse document frequency, that means it's got to learn how many times this word appeared in the entire data set. So it's actually training a model. And then the last vocabulary word is a pipeline. And a pipeline is just a series of steps. So I might transform, estimate, transform, estimate. Chain up a bunch of these operations together, just like I do in scikit-learn. So I could maybe take my data, make it binary. I could then do a vector assembler to take a bunch of columns in my data frame and make it into one mathematical vector that I could then apply linear regression to. And this is how machine learning will work. So without any further delay, I'd like us to actually get into, let me see here, how much more I want to go into vocabulary right now versus get you into a lab. Let's see here. Let's skip past some of this because I really want to get you to a lab again before lunch. Maybe you guys can take a look at these labs. I'm going to jump ahead. Notice there's different things here for transformations. You can do principal component analysis. That's just a transformation. Hashing. Normalized to fit a standard Gaussian. You could do polynomial expansions. Go forward a little bit. Clustering. These are estimators here. So we could do k-means clustering. We could do classification, like linear regression, Bayesian, decision trees. All sorts of algorithms available to us. Question?
So in the previous slide, I saw that LDAs on MLlib is not a thing. So does that mean that eventually it will be available on ML, on the DataFrames?
So LDA, latent Dirichlet analysis. Where did you see that was? Ah, yes. Okay, so at the time this slide was written, which is actually at Spark 1.6, it was not available. We can double check. They may have added it. They're adding new ones every day. So I got to go back and double check the documentation. Does anybody want to pull up the docs right now and see if they brought it into MLlib? It's available 6.1? 1.6.1, thank you. 1.6.1 added LDA. So they're adding more and more every day. There's a lot of engineering work being done to move those in. Question here?
Is the Python ML library at par with the Spark one?
So the question is the Python ML library at par with the Spark one? So all these algorithms get implemented first in Scala, and then they get called from Python. So what that means is often things get added first to Scala, and then a release or two later, the bindings for Python get added. And that's just the nature of the beast. So at this time, they just finished doing a big push to move, I think, 99% of them over. There may be one or two things missing. But I believe everything, for the most part, is available in Python. What you're lacking in the world of Python is some of the libraries that let you implement your own algorithms efficiently. For example, if you got to the step of writing something that needed gradient descent, that's not exposed in the Python side. But if you're writing a machine learning algorithm from scratch, why would you use Python at all? You want to use Scala, it's going to be faster. You want the guy who's using the algorithm to be able to use it from Python. But yes, most of these are available in Python. You will find a few things that are missing, and people scream, and eventually somebody submits a patch, and it gets into the next release.
We do take community contributions. So if you have something missing, if you want to do a PR, we'll look at that.
Let's see here. A few classification ones. Logistic, linear regression, isotonic regression. And there was a few others here. For collaborative filtering, we have alternating least squares and a number of other algorithms as well. More algorithms are being added all the time, but we're pretty selective. In terms of getting into the Spark product itself, we want your algorithm to be very robust and carefully vetted. How many of you guys worked with, what was the one on Hadoop? Mahout. So Mahout took community contributions without a lot of vetting. Some of them were good, some of them weren't so good. So they're really trying to vet the ones that come into Spark, but you can find third-party ones as well. If you just go to sparkpackages.org, spark-packages.org, you're going to find a number of third-party ones. We have lots of classifiers, binary classifiers, a huge variety of algorithms. I'm not going to read you this list. You've got a copy of the slides. What I want to do is get you into a lab before lunch again. So with that said, I'm going to call up Waleed here, who is our data scientist, and he's going to walk us through the first lab.
Okay. I think Doug just gave you a good idea why I am using Scala and have used Scala 100% of all the professional work that I've done. 100% of the time, machine learning on real data has been done in Scala. Faster, of course, but also the fact that DataBricks releases the Scala API first. It's the most up-to-date. It's the one that comes out first. A lot of the stuff under the hood is Java-based, but Scala is the way forward, as far as I'm concerned, at least. It doesn't mean you cannot use Python, but efficiencies, when you start using larger and larger data sets, you will see a lot of difference out there. On the other hand, if you're using Python, for example, for something like bioinformatics, you're not going to spend millions of dollars trying to port all the old libraries that already exist, not old, but all the libraries that exist from Python to Scala. So that's one case where using Python might be a good idea for you. But again, I think it all depends on you, your situation, your customer, where you're working, etc. Let's have a quick look at the lab. If you go to your DataBricks account here, you will find under Workspace one that is called MLlib data types. You can pick whichever one you want. I'm going to use the Scala one. Here we go. Can somebody give me a brief idea what is machine learning? How do you use machine learning, or how do you want to use machine learning? Just a very simple description of machine learning.
We use it for modeling, just to automate few things. I feed data and it predicts me later on so that I get the accurate one. I feed more and more data so that I get more accurate data. And as day goes on. Initially it will be a Spark, and then it goes on to give me an accurate, more accurate reality. So I use more of like the path.
Okay, so to you, machine learning is building a model of some sorts. And automating the process so it's easier to replicate, absolutely. Yeah.
It's an algorithm or statistical model that learns from data.
Okay.
As you put new data in and change it.
A model is basically a simplification of reality, right? And you want to automate that, and you want to make it better and better. Okay? So one of the things we will need for that is vectors. A vector is also, like a model is a simplification or a simple representation of reality. You need a vector to represent an entity, a person, a document. You are not going to take every piece of information about a person and implement it into your system. It might not be useful. So deciding how your vector is going to look like, or what kind of information is going to be there, is critical. So done. Have you all been able to get the lab? Looks good. Okay, two types of vectors. But basically, a vector is, at a very high level, a simple representation of something. A document, for example, we were talking about classification. You want to classify a document. How are you going to do that? It's not a simple, straightforward problem. So can we take the document, find a simplified representation of that document, and then use that information to do some analysis or some classification or run some algorithms? So how do you represent a document? For example, we can say just a simple count. I'm going to take each word, and I'm going to count the number of times it appears, and I'm going to use that number as the representation for word number 0, word number 1, word number 2, etc., and that represents your document. If I represent one document in my system, will I get a sparse vector, or will I get something else? A sparse vector means every element or most elements of your vector have a value. So let's say we have 1,000 words, and I've taken one document, generated a vector. Is it going to be dense or sparse, first of all? My whole universe now is one document, and I'm representing that in a vector. In this case, it's going to be dense because I only have 1,000 words, and that's all I know, and I've had only one document, so it becomes a dense vector. But now, let's say I'm not only representing one document. I have 1,000,000 documents. So basically, every single word of the English language possibly is part of this vector. So if I do that, I have every single word of the English language. Let's say 40,000 words to make it simple. Well, now the representation of a document going to be sparse or dense? It's going to be very sparse. Of course, depending on the application, you want to be somewhere in the middle. You're not going to take every single word of the English language and try to build a vector for it, because most of them are going to be empty, and you're going to have a sparse vector. Now, Spark-wise, a vector, a dense vector, is just a bunch of elements, a bunch of numbers represented. A sparse vector is a little different. You're basically saying, I have, first of all, here's the dense vector. You can go ahead and run that. And basically, it will create a vector with 3 elements. And while this is working, we'll take a second to attach and run. If I have 10,000 features, and I know that most of them are going to have no value, I don't want to reserve all the space for that vector. So I'm going to have a different type of representation just to, hold on a second, I need to run the whole, yep. Okay. We will get to the sparse vectors in a second, and then I'll look what's going on with the notebook in a second. Basically, 3 things that you need here to represent a sparse vector. One is the size, the number of features. The second part, the array that has the 2 and the 7, is basically which elements, which features of your vector have a value. So basically, anything other than 2 and 7 is going to be what? Empty. And finally, the values. The indices, 2 and 7, have a value. You go to the next array, it will show you the actual values 1 and 5. So that's, in a nutshell, how you represent a vector in Spark.
Waleed, I forgot, now is lunchtime.
Sure. OK.
So getting in between people and their food is a dangerous proposition.
OK. This is a good time for us to stop, and we can take off from this point. And I'll get a chance to have a look at that notebook. So if you don't have any questions, we'll see you after lunch. And how long are we taking an hour for that?
Starting at 1 o'clock. And then lots of hands-on and model building after lunch. So this morning was really meant to be orientation. After lunch, from 1 to 5, model building.